All right, let's work through the solutions to semester exam review number 2. This first problem involves identifying the dimensions of a matrix and then identifying a particular element within the matrix. So the way we do dimensions, it's always row by column. How many rows and then how many columns. We always state the dimensions in this way. So there are 3 rows. Rows run horizontally. So there are 3 rows and there are 2 columns. Columns run vertically. And so we would say that this is a 3 by 2 matrix. And the indicated element, this means in this matrix, what is the element that is in the second row? So in the same way that we do dimensions, this first number indicates the row number. So it's the second row and the first column, and the number that's in that position is the number 5. So that's our complete answer for number 1. For number 2 through 5, we're going to be doing matrix multiplication. Number 2 represents what we call scalar multiplication. And it's basically asking us to take the number 3 and multiply it by the C matrix. And so you can think the distributive property in a way, it's taking 3 and multiplying it by each individual element. So that's pretty easy. 3 times 4 is 12, and then 3 times -1, 3 times -3. On the bottom row, 3 times +3, 3 times 0, and then 3 times 6. And so that is your answer for number 2. For number 3, we're multiplying 2 matrices together, and before we can tell if that's even possible, we need to list the dimensions of each matrix. So letter B is a 3 by 2 matrix. Letter D is a 3 row 1 column matrix, 3 by 1. Well, to tell whether or not matrix multiplication is possible, you need to compare these numbers on the inside, and if they don't match, then you're going to say that this is undefined. Well, matrix multiplication is not possible in this case. It's only possible when these numbers match. So our answer for number 3 is undefined. Number 4, we'll do the same thing. So let's list the dimensions for the C matrix. It's 2 rows, 3 columns. The B matrix we've already identified, it's a 3 by 2. Well, in this case, the inside numbers do match, so we know matrix multiplication is possible. And these outside numbers have significance as well, because if the inside numbers match, the outside numbers will tell us the dimensions of the product matrix. All right, so let's just list out this C matrix: 4, -1, -3, 3, 0, 6, and we're going to multiply it by the B matrix: 2, -3, -2, 5, 3, 2. And matrix multiplication works like this. We can go ahead and set up a 2 by 2 product matrix. And this element represents row 1, column 1 of the product. So just think, I'm going to use row 1 of the left matrix times column 1 of the right. We always multiply row by column. So just match up the elements. 4 times 2 plus, then do -1 times -3 plus, and then do -3 times -2. And we just add those products together. So this is 8 plus 3, which is 11, plus 6 is 17. All right, and we're going to do that same process now to get row 1, column 2 of our product. So just think row 1 times column 2. And that's going to be 4 times 5 plus -1 times 3 plus -3 times 2. All right, 20 plus -3 is 17, and 17 plus -6 is 11. All right, now we'll work on the bottom row. This is row 2, column 1, so that's what I'll use. Row 2 times column 1. 3 times 2 plus 0 times -3 plus 6 times -2. 6 plus 0 plus negative 12. 6 plus 0 plus negative 12, and that's of course negative 6. And then finally, row 2, column 2, use row 2 times column 2. 3 times 5 plus 0 times 3 plus 6 times 2. So 15 plus 0 plus 12. 15 plus 12 is 27. And that is the answer for number 4. Okay, let's move on to number 5. And once again, we're multiplying two matrices together. So let's state the dimensions. A is a 2 by 2. C is a 2-row, 3-column. The inside numbers match, and so the outside numbers tell us that when we finish multiplying, we're going to have a 2 by 3 product matrix. So you might want to go ahead and just do blanks representing a 2-row, 3-column. And when I multiply these together, remember it's row times column. So to get row 1, column 1 of my answer, I'm going to use row 1 times column 1 from these matrices. 2 times 4 is 8, plus 3 times 3, which is 9, and you add those together and you get 17. Okay, to get row 1, column 2, use row 1 times column 2. So you're going to do 2 times negative 1, which is negative 2, plus 3 times 0, which is 0. Negative 2 plus 0 is negative 2. And then to get row 1, column 3, that's what we'll use. Row 1 times column 3. 2 times negative 3 is negative 6, plus 18, which is 3 times 6. And negative 6 plus 18 is 12. Bottom row, we'll use row 2 times column 1 to get this first element of row 2. 5 times 4 is 20, plus negative 12. You see how we got negative 4 times 3. So 20 plus negative 12 is 8. For row 2, column 2, that's what we'll use. Row 2 times column 2. 5 times negative 1 is negative 5, plus 0. Negative 4 times 0. So negative 5 plus 0 is negative 5. And then finally we'll do row 2 times column 3. 5 times negative 3 is negative 15, plus negative 24. And negative 15 plus negative 24 is negative 39. So that is our answer for number 5. Number 6, we're supposed to solve for this matrix called X using an inverse matrix. Before we do that, we need to do some subtraction. We're trying to get X by itself. So my first move is to subtract this matrix on the left side of the equation from both sides of the equation. And that's going to look like this. Just bring down this matrix multiplied by X. And let's show the subtraction. And we've got to be careful with the order. It's the right matrix minus the left matrix. 3 minus 1 is 2. 8 minus 9 is negative 1. 6 minus 3 is 3. And negative 6 minus negative 8 is 2. Now I'm ready to find the inverse, if it exists, of this matrix being multiplied by my unknown matrix that I'm solving for. And to find the inverse, it starts with identifying the determinant, because it could be that the matrix doesn't have an inverse. If the determinant is 0, then an inverse doesn't exist, and so there is no solution. So here's how I find the determinant. I multiply this way first. We call this the A element and the D element. So 12 times 3 is 36. And then I'll subtract the product of the other two multiplied together, which is 35. So there is an inverse that exists. The determinant is 1. And here's how I find it. If you want to call this the formula or the definition for finding the inverse of a 2 by 2 matrix, you multiply 1 over the determinant times this rearranged, changed up matrix. And then we'll do that in just a second. But I wanted to give you, again, the format for how it looks to get the inverse. All right, so maybe I'll change color here, and let's go ahead and apply this toward getting the inverse of this 2 by 2 matrix. So 1 over the determinant, and notice how D and A, or A and D, switch places. 3 and 12 switch places. The other two elements change signs. And multiplying by 1 doesn't change that. So I'll just go ahead and do it. 3, negative 5, negative 7, 12. We're going to call this the inverse of this matrix in our original problem. And to get our final answer, we're going to multiply the inverse times this matrix on the right, the matrix that we got after subtracting. So something to keep in mind is when you do this multiplication, you should always, it's very important, you will not get the correct answer if you do not put the inverse on the left side of these two. So before you multiply these together to get your final answer, make sure the inverse is the matrix on the left. And now we're going to do like we did in the previous problem. We're just going to multiply these two matrices together, row by column. So this row 1, column 1 means multiply row 1 times column 1. 3 times 2 is 6, plus negative 21 is negative 15. Row 1, column 2, 3 times negative 1 is negative 3, plus negative 14. Negative 3 plus negative 14 is negative 17. To get row 2, column 1, negative 5 times 2 is negative 10, plus 36 is 26. And then row 2, column 2 will be 5 plus 24, which is 29. And so that is my final answer for number 6. Okay, Cramer's rule says to basically for a 2-variable system, we're going to come up with 3 determinants. And the first determinant we'll just call D will be made up of, we're just going to do a 2 by 2 matrix using just the coefficients. All right, those are the numbers in front of variables. So 2, 4, 3, 5, and remember we saw in the previous slide how to come up with the determinant of a 2 by 2. You always start this way, 2 times 5, which is 10, minus, then go this way, 3 times 4, which is 12. So the determinant of what we would call the coefficient matrix is negative 2. Then we're going to do a matrix called D sub x, and the reason why we call it that is because we're now going to take these constants and we're going to replace the x coefficients with these constants. So in place of 2, 3, this first column, I'm going to put 10, 14. And I'm going to leave the y coefficients as they were. Now let's find the determinant of this red matrix. 10 times 5 is 50, minus 14 times 4 is 56. So D sub x is negative 6. So don't make the mistake that some people make and think that we found our answer for x. We found the determinant called D sub x. To find x, you always divide by this initial coefficient matrix determinant. So I need to divide by negative 2 to get my final answer for x. So x is 3, and I'll show my answer as an ordered pair. Now let's find y. So D sub y, just think this time we're not going to replace the x coefficients, we're going to replace the y's. And find your determinant, so multiply this way, that's 28, minus, now multiply this way, that's 30, and that's negative 2, but don't forget, you always divide by your determinant for that coefficient matrix, that first determinant that you come up with, and we get a positive 1 value for y. So my answer here is x equals 3 and y equals 1. Okay, this is the graph of exponential growth. So we got several things to do here. Graph the following function, providing a table of values with at least 5 points. Well, I want you to think of this as a parent function, and the parent would be y equals 2 to the x, but it's being translated, and the translation is going to be 3 units to the left and 2 units down. Well, first, to give us a table to work with, let's just make a quick table for the parent using these inputs: 0, +1, +2, -1, -2. All right, so if I let the exponent be 0, 2 to the 0 power is 1. If I let the exponent be 1, 2 to the first is 2. Exponent 2 gives me a y value of 4. Exponent -1, 2 to the -1 is 1/2, and 2 to the -2 is 1/4. All right, so that's the parent, but now let's show the shift or the translation of the parent: 3 to the left and 2 down. So we'll just call this table left 3, down 2. And to accomplish that from our table, to go left 3, that's like subtracting 3 from each of these x's. 0 minus 3, 1 minus 3, 2 minus 3, -1 minus 3, and -2 minus 3. And to accomplish down 2, we would subtract 2 from each of these y coordinates. 1 minus 2, 2 minus 2, 4 minus 2, 1/2 minus 2, and 1/4 minus 2. And this becomes the table that we will plot and connect the dots, and that will be our graph. All right, so we have -3, -1, -2, 0, -1, 2, -4, -1.5, and then -5, -1 3/4, and connecting the dots with a smooth curve. This is going to be the graph of this function, and it will continue to go up, of course, as the x values get bigger. And as the x values get more negative, we're just going to continue to approach this horizontal asymptote. So we're going to have to do this anyway. A horizontal asymptote, which is part D, is the line y equals -2. We're going to approach that forever, but we will never reach it. Okay, so let's go ahead and identify the other points. We did part A, that's the graph. Part B, is this growth or decay? Well, that is indicated by this number underneath the exponent. And if it's greater than 1, you have growth. If it's between 0 and 1, you would have decay. Okay, so let's do domain and range. So the domain, you can probably tell that every x coordinate available is going to be involved, as this graph goes forever left and forever right. So the domain will be all real numbers. The range, it does not go below, the graph does not extend below y is -2, but it goes forever above y is -2. So we will state it like this: all y such that y's are greater than -2. Not equal to -2, because we'll never reach that line y equals -2, but it will be all the y values above -2. And I believe we got all the things we were asked to do, so that's your answer for number 8. Number 9, this is an example of exponential decay. The word depreciates is another way of saying a particular item, in this case a car, is losing value over time. That makes sense. The more we use it, the less valuable it becomes. So exponential growth or decay, because you may see growth or decay on the exam, you always start with this basic function format. What determines the difference is how are we going to identify B, and in this case B is going to be a decay factor. That just means that we have an item that's losing value or depreciating. And when we want to find the decay factor, we always start with the number 1, and then we subtract whatever the rate of decay is. And in this case, that's 4%. Notice how I changed it to a decimal. So B is going to be 0.96. Now, just in case you see this on the exam, if we had an item that is growing in value, it's getting larger over time by 4%, then that changes this to a growth factor, and then I would be adding 1 plus 4%, and that would give me a B value of 1.04. So you'll need to read the problem and decide, is the item going down over time in value, or is it increasing in value over time? All right, so the A variable here always represents the starting value, the initial value of the car in this case is 40,000. We already established that B is 0.96, that's the decay factor. And then X, the exponent, will represent a certain amount of time that has passed. In this problem, it represents a number of years. So that is our answer for part A. And now for part B, we will take this, and all we have to do is plug in 6 as the exponent, replacing X, and then grab our calculator and let it do the rest of the work. So 40,000 times 0.96 raised to the 6th power is 31,310 to the nearest dollar. And so after 6 years, this car has gone down in value or depreciated down to a value of $31,310. Okay, we're ready for numbers 10 and 11. For these problems, we need to come up with another way of writing 9 and 27 using the same base in both cases. So for example, I know that I can represent 9 as 3 squared. So all I did on the left side of this equation was change 9 to 3 squared. But the trick is, since I used 3 as the base to represent 9, I also have to use 3 as the base to represent 27. And that's 3 to the third. And this is called the common base technique. So now that I've got common bases, I just focus on solving the exponents. Just let the left exponent equal the right exponent, and you'll get your answer. So after multiplying, this left exponent becomes 6x plus 2, and the right exponent becomes 9x minus 3. And solving for x, subtracting 6x from both sides, adding 3 to both sides, and then dividing by 3, we get x is 5/3. Okay, this number 11 is similar. I'm going to represent 256 using 4 to the 4th power. And on the right side, of course, 4 could be written as 4 to the 1st power. Don't really need the 1st power, but I'll go ahead and show it. And once again, once you get to this common base line, you just think about letting the left exponent equal the right exponent and solve. So I'm going to add 2b to both sides. I'm going to subtract 8 from both sides, and of course divide by 6, and we get our answer for number 11. B is -1. For number 12, we have this exponential growth problem. Kristen starts off the experiment with 7,500 bacteria cells, and then that number grows after 4 hours. So obviously the number is growing over time. We can think of these as ordered pairs where we let x represent a time, an amount of time, and y will be the number of bacteria cells that occur after that amount of time. So at the very beginning, we can think of no time has passed. There are 7,500 cells. After 4 hours, x is 4, they've grown to 23,000. Okay, so using y equals ab to the x power, we looked at that on a previous slide, we're trying to come up with b, which is in this case, it's going to be a growth factor. We already know that a is the initial value, which in this case is 7,500. That's how many we start with. So we're going to have to use this ordered pair to help us solve for B. All right, so using this ordered pair, y will be 23,000. A, the initial value again, or you can think of it as the y-intercept if you're looking at this ordered pair. A is 7,500, and we're trying to find B, and x out of this ordered pair would be 4. Okay, so solving for B, I'm going to divide both sides by 7,500. So let me grab my calculator, 23,000 divided by 7,500, and that is 3.06666. And now I'm just going to leave that in my calculator, and we need to do the fourth root of that. And an easy way to do the fourth root of a number, again, is to use this like an upside down V character and then put 1/4 in parentheses. That's just another way of doing this, the fourth root of a number. Okay, so I got that number still in my calculator. I hit the up arrow, upside down V, and in parentheses I'm going to put 1/4, and I get 1.3233. I'm just going to round that to the nearest hundredth. So my answer for the exponential function, which is part A, is y equals the initial value, 7,500, times 1.32 raised to the x power. And that's my answer for 12a. 12b, I will need to use this function, and x stands for, again, a number of hours that have passed. I'm just going to let x become 12. So it looks like this. Okay, calculator again, clear it, 7,500 times 1.32 raised to the 12th. And that number, rounded to the nearest whole number, is 209,869. 209,869. So there are 209,869 cells after 12 hours. And that is my answer for 12B. All right, 13, solving an inequality. This is going to involve changing these numbers, 16 and 8. We looked at some examples like this previously. We're going to use this common base technique. So I need a number raised to a power that equals 16. That's 2 to the 4th. So I just rewrote 16 as 2 to the 4th. And since I used 2 as a base over here on the left side, I'm going to also use 2 as a base on the right. So now remember, once you've got common bases, you just think about using the exponents in your inequality. So multiplying together, we get 8x minus 12 is less than 3. Add 12 to both sides, 8x is less than 15. X is less than 15/8. So once again, very handy to know how to use this common base technique. All right, number 14, similar problem. This time I'm going to rewrite 1 over 625 using a base of 5. Okay, 5 to the first, of course, is 5. And I know that 5 to the 4th is 625, but if I make it to the negative 4th, I get the reciprocal of that. So once again, 5 doesn't need to be changed, 3 minus 2x, but my common base is 5, so that means to make it equal 1 over 625, I'm going to raise 5 to the negative 4. Okay, now I just focus on the exponents. Let those be part, or they will become the inequality that I will solve. All right, so I'm going to subtract 3 from both sides. And now I'm going to divide by negative 2, and then we got to remember whenever we divide or multiply by a negative number, when an inequality is involved, we have to switch the inequality direction. And so my answer here will be all the numbers less than 7/2. That's my answer for 14. All right, number 15 involves summation or sigma notation. This is the capital letter sigma. When you see that in math going forward, you'll know it stands for the sum of. And what this means is this represents a way to come up with the terms of a series. And this means let's add up all the terms in this series. Well, first of all, how many terms are there? If you want to know the number of terms from sigma notation, just take the top number of sigma, 7 in this case, subtract the bottom number, which is 3, and then always add 1. And just always do a plus 1 because you're going to be counting 3. Just think about counting 3, 4, 5, 6, 7. Well, that's 5 numbers, 3, 4, 5, 6, 7. And when the numbers get really big and you don't want to have to do a whole count, you can always do this little process. Top minus bottom, and then always add 1, and that will give you the number of terms. The first term can be found anytime by taking the bottom number, in this case 3, and replace k in this expression and simplify. Okay, so to find the first term, I'm going to evaluate this. 1/2 times 4 to the second power, 3 minus 1. Okay, 4 squared is 16, and 16 times 1/2 is 8. So the first term in this series is the number 8. To get the last term, I'm going to take the top number of sigma, and I'm going to put it in for k and evaluate. So I'm going to do 1/2 times 4 to the 6th power, 7 minus 1. So 4 to the 6th is 4,096, and basically divide that by 2 or multiply by 1/2 tells us that the last term is 2,048. To get the sum of a geometric, this is a geometric series, we're going to use this formula. The sum of a certain number of terms is going to be found by doing the first term times 1 minus the ratio raised to the nth power over 1 minus the ratio. Well, n in this case is 5, that's the number of terms. A sub 1 stands for the first term. R stands for the ratio, and R is always the number. If you're looking at summation notation, R will be the number directly below the exponent. So in this case it's 4. So we can find the sum of these 5 terms pretty quickly. The first term of 5 multiplied times 1 minus 4 to the 5th divided by 1 minus 4. Okay, so grab your calculator. 5 parentheses 1 minus 4 to the 5th power. And then I would just divide by -3. And I just realized I used 5 as the first term, so I'm sorry about that. That's the number of terms. The first term, of course, is 8. So I need to be a little more careful. Okay, so let's try this again. 8 times 1 minus 4 raised to the 5th power divided by -3 is 2,728. And that is the sum of those 5 terms represented by this series. All right, moving right along. I need for you to know for this exam the properties of logs, like the power property, the product property, and the quotient property. Well, number 16 is a perfect example of using the product property, because using the fact that log base 4 of 3 is given and log base 4 of 5 is given, I can rewrite log base 4 of 15 using the product of 3 times 5. Okay, I haven't changed anything as far as the value. I've just rewritten it in an equivalent way using multiplication. And the product property says this: I can expand the multiplication of these two numbers into 2 separate logarithms using addition. Log base 4 of 3 plus log base 4 of 5. So in general, the product property says this: if I have 2 logs of the same base, that are being added together, then I can put those together as a single log using multiplication. And what we're doing is the reverse of that. If I have a single log of a base that is representing two numbers being multiplied together, I can break those up using addition. Okay, so now that I have the decimal approximation of each of these, I'm just going to add these two decimals together to get my answer. So 0.7925 plus 1.1610, and I grab my calculator, add those together, and I get 1.9535. And that's my answer for 16. For number 17, this is an example of the quotient property. And it says this: two numbers, if I have a log of two numbers that are being divided, then I can break those up using subtraction. So the product property involves the addition of two logs. The quotient property involves the subtraction of two logs. So I can write this using two separate logs and the top number being subtracted by the bottom number. All right, so I use those same two values. Log base 4 of 5 is 1.1610. Log base 4 of 3 is 0.7925. And I just subtract these and I will have my answer. .3685. And that is our answer for number 17. Okay, more practice with those log properties. When we solve log equations, they become very necessary. In order to solve a log equation, I have to take multiple logs and condense them into a single log. Well, here again is the product property. These have the same base, so I can write this as one single log, base 3, of 6 times x. And here's another property of logs. This is called the log property of equality. Okay, if I have just an equation that is one log equal to another, and as long as the bases are the same, I can essentially just let these numbers 6x and 12 equal each other and solve for x. So my answer for number 18 is x equals 2. That's the log property of equality. Now that's only for when it is one log equal to another and the logs have to be the same. Okay, so let's try number 19. First of all, I'm going to take these two logs, base 7, on the left side of the equation, and I'm going to write them as a single log using multiplication. So I multiplied 100 times y plus 5. Okay, and once again, I've got this log property of equality, so I can essentially just think about the log base 7s being taken out, and I'm going to solve 100y plus 500 equals 10. So 100y equals negative 490, and y will be negative 490 divided by 100, and that's negative 4.9. All right, moving right along. Now we have some exponential equations, and the rule of thumb is exponential equations need to be changed into log equations. All right, so here is number 20 written as a log equation. Log base 5, it's base 5 because that's the base for the exponent, of 9 equals x plus 2. You always let, and when you're writing a log equation, you always let the log equal the exponent. And now we're going to use this change of base formula, which says log of the top number divided by log of the base. So let's do log 9 divided by log 5. And I got 1.36521238.9. I'm just going to leave that in my calculator and subtract 2 to solve for x. and I end up with x is negative 0.63, and the directions I think said to, round to the nearest 10,000, that's 4 decimal places, negative 0.6345, and that's my answer for number 20. Number 21 is an inequality, but the same thing is true. Exponential inequalities need to be written as log inequalities. So log base 3 of 4 to the x power. Notice the inequality is pointing at the exponent, so when I rewrite it, it still needs to be pointing at the exponent. Okay, so I'm going to use this power property, which says that I can bring this exponent down and use it as a multiplier. And now I'm going to use this change of base property again, which says log 4 divided by log 3. So log 4 divided by log 3. That's 1.261859507. X, just going to go ahead and round it to 10 thousandths. 1.2619. X is greater than or equal to x minus 1. And now to solve for x, I need to get the x's together on the same side. So I'm going to subtract 1x from both sides. So it's like 1.2619 minus 1, which is 0.2619x. So I'll just show you what I did here. I just subtracted 1x from both sides. So 1.2619 minus 1. And that's going to be greater than or equal to negative 1. And so now to solve for x, I divide negative 1 by 0.2619. And I get negative 3.8183. So x is greater than negative 3.8183. Moving on to number 22. This is another exponential equation, but I notice that it's base e. So I got to be careful when I turn this into a log equation, I'll make it into a natural log. But first things first, I need to isolate e to the x first. So my first move is to add 2 to both sides. I need to divide by 3 on both sides. And this is pretty obvious because anything to the 0 power is equal to 1. But just for the sake of consistency, here is what this would look like as a natural log equation. Natural log 1 equals the exponent, x. So if you did use your calculator and do natural log 1, you would get 0. So my answer for number 22 is x is 0. Okay, this is a log, a natural log equation. It needs to be changed into exponential form. The base of the natural log is e. So I'm going to do e to the 5th power. And notice the inequality is pointing at the exponent 5, so it still should be pointing at 5. And I'm going to let that equal x minus 3. So in my calculator, I'm going to do e to the 5th power. So find your e to the x button. So it's second ln on the TI-30. And then let's put 5 as the exponent. So I got 148.4131591. Don't need to write that down. I'm just going to do plus 3 to that number. And my answer, after I add 3, I got 151.4132 is less than x. I like to turn it around and say x is greater than 151.4132. So you need to be good at taking exponential, making it log, or taking log and making it exponential, and then know how to solve from there. All right, number 24, another problem practicing the log properties. So these numbers like 3 and 2 and 2, lower subtracting, Before we can combine these into single logs, we need to make these become exponents. So natural log of 4 to the third, that's 64, plus natural log 2 squared, that's 4, minus natural log 3 squared, that's 9. Okay, just going left to right, I've got two logs that are both base e. Two logs that are being added can be written as a single log using multiplication. And 64 times 4 is 256. Two logs that are being subtracted can be written as a single log using division. And 256 divided by 9. And that's as far as we need to go. We can't reduce this. And we did as the instructions asked. We wrote it as a single logarithm. Finally, we have this problem, this compound interest, and the interest is compounded continuously. So you need to be aware that when interest is compounded continuously, this is the formula that we're going to use. So A means how much did we end up with, principal plus interest. P is how much did we invest. So we're going to try to find a $7,000 investment. R is the rate as a decimal. And T is the number of years, so that's 12. So that's not a decimal here, that means times. Okay, so we'll just grab our calculator and let it do the work, 7,000. And then we're going to do second ln. That gives us e to the power, and then the parentheses, the exponent for e will be 0.053 times 12. And that ends up being $13,222. And for these interest problems, we typically round them to the nearest penny. That's 37 cents. That's your answer for 25A. Now 25B is a little different. How long would it take? In other words, what would T be, how many years, to take 7,000 and make it become 21,000? All right, so A is 21,000, P is still 7,000. The rate is the same. We're trying to find T. So again, just like we did on the previous problem where we're trying to isolate E to the power, we're doing that same thing here. So divide by 7,000. And now this exponential equation with the base of e needs to be written as a log equation. Natural log, remember, anytime e is the base, you're going to use the natural log. Natural log 3 is equal to the exponent 0.053 t. So in your calculator, natural log 3 equals, and I would just leave that number there, and you're going to divide by 0.053. And we get 20.728, but we're going to say approximately, we're just going to round to the nearest year, we're going to say about 21. So the answer to the question, it would take about 21 years for, at this rate, for 7,000 to become 21,000. And that's it. That is review number 2. So I hope you're studying hard. I hope you're having good understanding. And if I can help you more, let me know.